Assalamu alaikum dear students. Today we will continue with the photophosphorylation, especially the non-cyclic photophosphorylation. And previously I told you about the mechanism of primary photochemical reaction. And today we will continue with this process. That is how the non-cyclic photophosphorylation takes place. So for that purpose, we have to take into consideration both the pigment systems, that is pigment system first and pigment system second, and light will be illuminated on both the pigment systems simultaneously. Now in the thylakoid membranes there is a series of various agents in addition to the pigment systems, and they act as electron carriers of the photosynthetic electron transport chain. And also there we have to take into consideration a redox potential scale. But given the conditions, the stationary is not adequate. Here we have a small board here because of the lockdown effect, and that is why I cannot manage to show here the redox potential scale. So skipping that part of this exercise, we will continue with the two pigment systems and the arrangement of various other agents in the thylakoid membrane in order to complete the mechanism of this non-cyclic photophosphorylation. So first of all, what we will do, we will here draw the pigment system second. And this pigment system second, you already know that it has a reaction center P680. And this has a definite redox potential value, and it contains the manganese protein here, manganese protein, and also there is water as a raw material for photosynthesis. And these are the various pigment molecules that are tightly packed here in the pigment system second, and they include both the antenna molecules and the core molecules, and light is incident upon them. These are the photons that are being captured by the pigment molecules, and then ultimately the light is to be transferred to the reaction center P680. So this is P680 in the ground state. Now P680, that is the reaction center of this pigment system second, I will show here in the excited state. Here in the ground state, this acts as a poor oxidant and poor reductant, but the excited P680, it becomes a strong oxidant and strong reductant, and it is by virtue of light. After this P680 excited pigment molecule, there I will show you the pheophytin. Pheophytin is actually the primary acceptor in the pigment system second, and this is actually a colorless chlorophyll that lacks the magnesium in the center of porphyrin head. Pheophytin is a colorless chlorophyll. After pheophytin, there are various quinones. For example, we have quinone A, quinone B, and then there is an important quinone that you call as plastoquinone. So I am showing here the plastoquinone. Then there is another agent that you call as cytochrome B to F complex. So I will show here cytochrome B to F complex. I have already told you about this complex, that there are two units of cytochrome F, one unit of there are two units of cytochrome B, one unit of cytochrome F, and also there is an iron sulfur protein. In addition to this, there is plastocyanin, a copper containing protein. Then there is pigment system first, PS first is here. Its reaction center is P700. Reaction center of the PS first. and it has also its constituent core and antenna molecules, and the light will also be incident upon these molecules. This is here P700 and P700 in the ground state, and when this gains a sufficient quantum of light energy, it will be excited. So excited P700 will be shown here. It is marked by means of a star, asterisk mark. So this is P700, which is in a state of excitation, excited P700. Okay, now after this I have to show in the thylakoid membrane the primary acceptor in the pigment system first, and that primary acceptor in the pigment system first is a phyloquinone. Phyloquinone, and phyloquinone or vitamin K is present in the thylakoid membrane, and after this there are many quinones, and there is also a series of iron sulfur proteins present in the thylakoid membrane, and one important iron sulfur protein is the ferredoxin is present after those many iron sulfur proteins and after those quinones. Now this ferredoxin is an important iron sulfur protein present in the thylakoid membrane, and there is also present a substance that you call as FNR. FNR is a substance. This is called as ferredoxin NADP reductase. This acts as a protein or an enzyme, and here I am drawing NADP positive, that is nicotine amide adenine dinucleotide phosphate, and this has a positive charge here, and this is associated with ferredoxin, and there is also present this FNR, that is the ferredoxin NADP reductase substance. Now let us start what actually happens during the non-cyclic photophosphorylation. I earlier told you that both the pigment systems will be simultaneously illuminated by light. So when pigment system second is illuminated by light and the reaction center which was so far in the ground state gains a sufficient quantum of light energy, it becomes excited. This thing I have said to you already in the mechanism of primary photochemical reaction. That is the P680 is excited, and this P680 now emits an electron, and that electron goes into the pheophytin. Pheophytin is thus reduced, whereas P680 is oxidized. Now when P680 is oxidized and pheophytin is reduced, this oxidized P680 strongly attracts an electron from manganese, because the hole created in it is to be filled up quickly, and manganese for that purpose furnishes the electron to P680, and this manganese also develops a hole or electron debit in it, and it strongly attracts the electron from water. So water needs to be photolysed. Water needs to be photolysed, and it will be split into half of O2 plus 2 electrons plus 2 protons. So this is called as photolysis of water, and the details of this photolysis of water I have already told you. Now This oxygen which is liberated here, it will escape into the atmosphere, because you know that green plants liberate oxygen into the atmosphere during the process of photosynthesis, and that is this oxygen. The two electrons, they will go into P680 via manganese, one by one, and finally these are accepted by pheophytin, and pheophytin gives the electrons to rest of the agents turn by turn. So this was the fate of electrons of water. Now we have protons. The protons which are here produced will be channelized towards the thylakoid loculus. Earlier I have told you about the structure of thylakoid membrane. Suppose this is the thylakoid membrane, and this space enclosed in the thylakoid membrane is called as loculus. Loculus. And the protons generated because of photolysis of water go into the loculus. So these go on accumulating inside the thylakoid channel or inside the loculus. Now come to this point. When P680 was excited and it gave electrons to pheophytin, at that time there were two options. One option was that P680, which was excited, it could regain the ground state. How it could regain the ground state? It was because of quenching the fluorescence to itself. That is, P680, which was excited, it could lose the electron. The electron which was excited to the higher energy orbital, that could come to ground state by losing the previously absorbed energy in the form of long wave radiation. That is, there would have been a red light emission that you called as fluorescence. This was one option to ensure the fluorescence. Another option is that it could have given its electron to pheophytin. That is, it could have quenched its fluorescence to primary acceptor, that is pheophytin. And this is another option. Now, what option or which option out of these two is likely to happen? The option second is likely to happen. This is because the speed of this quenching of fluorescence of excited P680 to the pheophytin is several orders of a reaction faster than the speed of that reaction where P680, which was excited, would go into its ground state. That is, it could ensure long wave radiation fluorescence. So this reaction is more fast, I mean to say faster. That is why this happens here. And in nature you see that the green plants never emit the red light. This is because they do not show the fluorescence because of presence of this primary acceptor in the S1 state, first excited singlet state, and it quickly captures the electron from P680. Thus pheophytin is reduced, but this pheophytin will give the electron to quinone. Suppose here we have quinone A, quinone B, and these will receive the electron, and they will finally give the electron to plastoquinone, which is an important quinone in the thylakoid membrane. But plastoquinone, in order to be completely reduced, requires 2 electrons and 2 protons. And 2 electrons will be given to it from these quinones one by one. That is, in the first event, 1 electron will be given to it, and in the second event, another electron will be given to it. And this will receive the protons, 2 protons from stroma side. Suppose here we have stroma, this is the thylakoid membrane, and 2 protons will come from stroma part, and they will go to the plastoquinone. And plastoquinone, I have already told you that it is a mobile electron carrier. It keeps on moving from outer edge of thylakoid membrane towards the inner edge of the thylakoid membrane and returns towards the outer edge again. So in this process, this plastoquinone will get fully reduced. I will show it here. Suppose we have this plastoquinone, and this plastoquinone has now received what? 2 electrons and 2 protons. The electrons are coming from this pathway and the protons are coming from the stroma side, and in this way PQ is converted into PQH2. That is plastohydroquinone. Plastohydroquinone is again converted into plastoquinone, but in doing so it has to lose both the electrons and both the protons. When it loses the protons are pumped into the loculus of the thylakoid. So these 2 protons join the protons that came from photolysis of water. And the electrons, here 2 electrons are to be handed over to the cytochrome B2F complex. So here I will show you this plastoquinone giving the electrons, giving the 2 electrons to cytochrome B2F complex. Here you have to remember one point, because the electrons are coming from plastohydroquinone to cytochrome B to F complex, and plastohydroquinone is thus converted again into plastoquinone. So cytochrome B to F complex now receives the electrons, and in this case only cytochrome F and iron sulfur protein will participate. Cytochrome B does not participate. cytochrome B जो है अभी वो participate नहीं करेगा, बल्कि जो ये electrons हैं ये किस में जाएंगे? They will go into iron sulfur and then into cytochrome F. And the cytochrome B to F complex will pass these electrons to another agent that you call as plastocyanin. So electrons will go into plastocyanin, and then finally plastocyanin, which is a copper containing protein, it will give the electrons to pigment system first, especially to the P700. So electrons will go into P700. So this was about the detail of journey of electron, that you call as downhill journey of the electron, while it came ultimately from water and entered into pigment system second, and then into pheophytin, then into quinones and plastoquinone, and then into cytochrome B to F complex to plastocyanin, and then into pigment system first, especially to its P700. Now keeping this thing in view, now let us consider when this P700 was in its ground state. It was initially in the ground state and light was incident upon it. And this P700 also got excited at that time. When it got excited, it had a primary acceptor, that is phyloquinone, and it gave the electron to phyloquinone, and this was oxidized, whereas the phyloquinone got reduced. This was the primary photochemical reaction associated with pigment system first. Now phyloquinone will give electron to the agents in the thylakoid membrane, which are various quinones and iron sulfurs, and performing the journey through these various agents, the electron will now go into ferridoxin, an iron sulfur protein. and this ferredoxin will give the electron to what? NADP positive. NADP positive. When NADP positive receives the electron, it receives it via this enzyme that you call as FN or ferredoxin NADP reductase. And when it gets one electron, NADP is converted into NADP positive is converted into NADP. So this positive charge was removed, or we can say it is electron debit, or hole was filled by the electron coming via this chain. So it got converted into NADP. Now you see that another electron will be here emitted, and that too will perform a downhill journey, and this will become NADP negative when it accepts another electron. And now it also receives two protons, and those two protons will come from the loculus of the thylakoid. Suppose here we have this loculus. I am drawing it here. This is the loculus, and this is the thylakoid membrane. In the thylakoid membrane, there is present F0 to F1 complex like this. This is F0 part and this is F1 part. This becomes the elementary particle. This is loculus where protons are present, and they have built up to generate a proton motive force, and that proton motive force pushes the protons via this particle that you call as F0 to F1. These protons will perform many works. One work is that they will go and join this NADP negative. If one proton goes here, this becomes NADPH. If another proton mixes with this or combines with this, it remains as H positive. So this is the generation of NADPH plus H positive. NADPH plus H positive, which is reduced nicotine amide adenine dinucleotide phosphate, which is said to be the reducing power. So this will be called as reducing power. It is now generated here. Now, in order to generate complete assimilatory power, what happens? The protons which come from loculus of the thylakoid via F0 to F1, they will here they will help us in generation of ATP, adenosine triphosphate. That process you call as photophosphorylation. The generation of ATP in the chloroplast in the presence of light will be called as photophosphorylation, and this time we are actually studying about non-cyclic photophosphorylation. Now what happens in the non-cyclic photophosphorylation? I will create a space here in order to show it. Suppose we have here this loculus which contains the protons like this, and here you have F0 part, and this is what? F1 part, that is F0 to F1 complex which is present here. Now through this F0 to F1, what happens? Two protons come into the stroma part, and here in the stroma we have adenosine diphosphate negative present already there, and there is also present H3PO4. H3PO4 is actually the phosphoric acid, and if we draw this phosphoric acid like this, let us draw it, phosphoric acid like this. We will draw it POH, OH, OH, double bond O. So this is the phosphoric acid. Now, these two protons will take one of the oxygens of phosphoric acid with them. And when this oxygen moves to two protons from the phosphoric acid, it takes two electrons with it. That is, it is ejected as O negative negative. And this O negative negative combines with 2H positive to generate H2O. That is, there is formation of metabolic water. Metabolic water. Because of this formation of metabolic water and because of striking out of an oxygen, O negative negative, what happens here? This remains as H and this develops two positive charges upon it. So this phosphate is H3PO3 plus plus. H3PO3 plus, sorry, H3PO3 plus plus. This is said to be activated phosphate. इसको हम क्या बोलेंगे? It is called as activated phosphate. Now this activated phosphate having two positive charges upon it, and ADP divalent negative having two negative charges upon it, these two readily can combine with each other. In the presence of this F1 part, this F1 part thus acts as ATP synthetase enzyme. ATP synthetase enzyme, or you can call it as coupling factor. Coupling factor, because it couples ADP negative negative with activated phosphate and it forms ATP. So when one proton was moving from loculus towards the stroma, one ATP got formed. Similarly, if another proton pair comes out to the stroma, this whole process will be repeated and another ATP molecule will be generated. So this is called as photophosphorylation. And this mechanism of photophosphorylation, that is formation of ATP, was given the name of chemiosmotic coupling. इसका नाम रखा गया क्या? Chemiosmotic coupling. It was called as chemiosmotic coupling, and this mechanism was given to us by Peter Mitchell in 1960s, and Peter Mitchell was also awarded a Nobel Prize for this work. So this is said to be chemiosmotic coupling or chemiosmotic synthesis of ATP in the process of photophosphorylation. Now again come to this non-cyclic photophosphorylation. Here we have P680, that was in the ground state. This is PS second, this is manganese, this is water, and water was photolyzed to form half of O2 plus 2 electrons plus 2 protons. The electrons go into the PS second, especially P680, to fill the hole, and then this generates this process that you call as non-cyclic photophosphorylation. Basically, what was the task in this process? The task was this water was to be oxidized, and electrons and protons needed to be removed from this, and this NADP positive, which is a coenzyme, this needed to be reduced. that is the electrons and protons coming from water were to be given to NADP positive to render it reduced NADPH plus H positive. But this substance was thermodynamically very difficult to be reduced. And this substance, that is water, this too was thermodynamically very difficult to be oxidized. But all this became possible because of this arrangement in the thylakoid membrane and because of participation of light, that is non-cyclic photophosphorylation. Suppose we have some at some point there is fire, a burning fire is there, and water is very far away and there is no fire brigade available. This is an example. If water is very far away from the site where fire is in an active state and we want to extinguish the fire, what we will do, we will arrange a few men from the source of water towards the fire, and then each turn a person carries or works out a bucket of water from the well or from the water body, and it hands over this bucket of water to another person, that hands over to another person, and similarly this makes a chain of the agents or persons who carry the bucket of water to the site of fire so that the fire will be extinguished. So this is rather a sort of bucket brigade instead of fire brigade. So similarly we have arranged these so many agents here in the thylakoid membrane, and these act as the agents of agents for carrying the electron from water to NADP positive. So this is non-cyclic photophosphorylation because here electron, ultimate source of electron is water, and it finally goes into NADP positive so that NADPH plus H positive is formed, and electron has no chance to come back. That is why it is called as non-cyclic photophosphorylation. And since this non-cyclic photophosphorylation is to be arranged as per the redox potential values of these agents, why we arrange them like this? This is because they have their own redox potential values and we have arranged them accordingly, and this forms a zigzag pattern. Because of this zigzag pattern, Hill and Bendel called this as Z scheme. Z scheme. It was Hill and Bendel who gave this name Z scheme in 1960s. 1960s. So this was about the non-cyclic photophosphorylation. We will continue